Okay, this week we're going to look at modeling, and in particular we're going to look at modeling by hierarchical kinds of models. So what we want to do is look at objects where the objects can relate to other objects, or the objects could have sub-objects, and those sub-objects could have other sub-objects. So for example, if I'm making a model of a robot and the robot has one arm, as we'll see in our first example, or it's more of a model of a figure in some sort of humanoid robot that has arms and legs, those parts all relate to each other, and rather than specify and control each part individually, graphically, or in some model or simulation, we'd like to incorporate the relationships that we know exist between the parts of the model. So we'll look at a couple of approaches to that in today and in this lecture and in the next lecture, and after that we'll extend these ideas to more general hierarchical modeling techniques, which will get us into talking about scene graphs. Okay, so let's start with this, that we want to look very briefly at why the kind of models we've been working with so far are somewhat limited, but we'll talk about at least a way of building a model that we can transport from place to place. We want to then we'll introduce hierarchy, in particular articulated models where the parts are connected by joints, as we would have in a robot or a figure that we use in an animation. And then in order to implement that, we'll look at tree structures for doing that, in particular in the next lecture, and look at directed acyclic graphs, which are pretty much equivalent, and see that we can model abstractly with a graph, but then implement an implementation of that graph to then do the graphics and do the animation. Okay, so let's start with something very simple, is that if I have some objects, we've argued that we could build up models with prototype objects which we generally used to be called, we don't use this term too much anymore, they used to be called symbols. And they could be things like the cylinder that you see here, or a cube, or a sphere, or a cone, or something that in another context might be appropriate for that. If you're doing, say, VLSI models, you would have symbols that would be appropriate to that application. And then for each one, now each of those we've said would exist in its own frame. So we would have what we call model coordinates that describe it in a frame. So typically that object would be, or symbol would be, defined in a convenient way within its own frame. So for example, with the cylinder here, we might orient it with the y-axis, and then either have the base resting on the plane y equals 0, or center it, and it might have a unit radius and a unit height, or any other convenient value. So the cube, the obvious one would be to center it at the origin and have it have sides of length 1 or sides of length 2. And then we've talked about the instance transformation. So each symbol has a transformation applied to it, which brings it in to the object coordinate system. And generally that's scale it up to the size you want to be, orient it the way you would like it oriented, which is a rotation matrix, and then translate it to where you want in the world. So this frame over here would be the world frame. This would be the model frame on the left. So you can think of a model then as in terms of a big table. If we were to number our symbols, we could say 1 was a cube and 2 was a sphere. We could just have a table that listed all of the symbols that were in our model by their IDs, and for each one we would have an associated instance transformation that would bring it into the model. So we could either have a homogeneous coordinate matrix there, or we could just put in the scale factors in the x, y, and z directions. We could put the rotation angles about the origin, and we could put in the translation components. So we would essentially have 10 entries that would describe each object that was in that model. And that's pretty transportable. It's not WebGL or any other system. It's simply a table that could be written in ASCII or any other code and transport it around. Now, the difficulty with that is, as we started, is that that doesn't show any relationship between any of the objects or symbols that are in that scene. So if you look at something really simple like a car that's moving forward, you can see two types of relationships here. First, that if you look at the wheels, we're just going to say there's 5 basic parts. There's a chassis which sort of moves as a whole, and there's 4 wheels that rotate. So the first thing you notice is, well, the 4 wheels are identical, so we only need 2 symbols to build up this model, a chassis symbol and a wheel symbol. Of course, they could be made up of simpler things, but let's think of a wheel symbol and a chassis symbol. And second, that the motion is coupled. If you know how fast the wheels are turning, then you know, and they're all going to turn, in the first approximation, they're all going to turn at the same rate. We know how fast the car is moving forward, and likewise, if I know how fast the car is moving forward, I can then determine how fast the wheels must be rotating. And if I then just have a table as we had up here and says, oh well, you have symbol 1, the tire 4 times, and the chassis 1 time. Sure, I can build up a model like this, but it doesn't take advantage of the 2 observations that we just made, the identity of the 4 wheels and the fact that the motions are all coupled together. So if we start looking how we might write some program in pseudocode that controls it, it would be something, like we would have something that says car, we give it a parameter, which is how fast it's going, and then we could draw the chassis, draw the right front wheel, left front wheel, the right rear wheel, and the left rear wheel, and that's precisely what we don't want to do. This is again showing, well, we have only 2 functions, a chassis function and a wheel function, but and what we would then do is position each one in the correct place, but still it's not showing the relationship between the motion of the chassis and the motion of the wheels. So we want to really have a better way to look at that, and we're going to do that by introducing some very simple graph notions. So let's say, okay, general graph is just a bunch of nodes and edges, sometimes called links, that connect them. Those links may be directed where they have arrows on them, as you see here, where we go from one node to another node. That's a directed graph or an undirected graph. Generally, we're going to be talking about directed graphs here. And a cycle is a directed path that starts at one node, goes to another, and eventually comes back following the arrows to the original node. So here would be a cycle or a loop over here in red. And this is going to also be important as we try and implement that. Now, we're not going to need, at this point, to talk about general graphs. There's really the particular kind of graph we're going to spend most of our time with is a tree, and I suspect all of you have had at least some beginning data structures where you study simple trees, and that's all we're going to need is a very straightforward tree. So a graph is a tree, and it's a connected one. We're not going to have a bunch of subtrees floating around, where every node except the root node has a parent and leaves without children. So you have a parent and you descend down to the children. We can think of those now as being directed paths from a parent to a child, from a child to its children, and the terminal nodes are the leaves of the tree, and we call them leaf nodes or terminal nodes. So there's a simple tree, and we'll work with that a fair amount. So now, if we want to say, okay, we know what a tree is, how do I use that to model the car that we've been talking about? So let's apply that and say, well, okay, if we say that the chassis is the root of that graph, and the wheels are connected to it, then I could say, okay, the chassis has 4 children, which are the 4 wheels. And you can start seeing some of how we're going to convert this into a model we can use with graphics. So for example, if we want to convert this to graphics, then somewhere in this node we can store information, in particular the geometry of the chassis, and in the child nodes we could store the information about the wheels. They're cylinders of some sort with maybe some embellishments, and we can then need a way of describing how we go from a parent to a child, and we can store that information either in the parent, or we might want to store information on these links. That's possible, and we'll see that as we go along. But you can see how this can be converted directly into the kind of pseudocode that we had a minute ago for the car. Now, if this doesn't take advantage of the fact that the four wheels are the same, if we want to use the fact that the four wheels are the same, we can replace this tree by what's called a directed acyclic graph. So what a directed acyclic graph says is that the links all have directions, but there are no loops in the graph. You cannot get back to where you started from by following these directed links. So here's the chassis, and all four, it has four links going from it, but all four go to the same place because all the wheels are identical. And this is not a tree anymore because the wheel has essentially four parents, but you can't circle around because there's no links leaving the wheel that get you back to the chassis. Now in practice, that's not much different than dealing with a tree. In terms of writing code for a directed acyclic graph, it's generally pretty much the same as writing code for a tree, so we don't really need worry about the difference between this model and this model up here. I'll tend to draw things as trees, but realizing that a lot of the nodes may all point to the same eventual object that we want to draw. Okay, now let's talk about doing some simple model. Okay, first is the point I made a few minutes ago, which is where we place information. And we can do it in a number of ways. In the node, you're going to have to say, well, where are the children? So you're going to need the equivalent of a pointer to its children. And what you want to store in a node is almost always what it is you want to draw. What's the geometry of what that node describes? And the edges now are going to have information. The important word in here is incremental. Is that you don't need to know how to store in each edge all the information about how you got there from the root node. All you need to store there is information about how you got from its parent, as long as its parent has information how it got to its parent, and so on. And this information can be stored on the nodes or on the edges. What we're going to wind up doing, at least in the examples I'll give you today and in the next lecture, are storing all of the information in the nodes. It'll tell you what it is you have to draw, and it'll point to what you have to draw and say where are the children and children of that node. So the example I'm going to show you, and their code for this is on the website for chapter 9, is a robot arm as our first example of an articulated model. I'll show you the example in a minute or two about the implementation we have on the website. But I built it out of cubes that have been distorted into right parallel pipets, just because I didn't want to put a cylinder model in there. We will talk about modeling cylinders and other quadric objects a little bit later. But we can think of it as consisting of three basic parts, each of which is defined in its own system. We have the base, which is a cylinder, which in its own system could be sitting on the y=0 plane, centered, the bottom centered at the origin, and it now has 1 degree of freedom. All it could do is rotate. Now all of these are very simple connections. It just can pivot at a connection point over here. So the lower arm and the upper arm are just little instances applied to a cube that creates these parallel pipets, which we can assume are sitting Also sitting on the plane y equals 0, or if you want, could be centered at the origin. That isn't crucial. And all they can do is rotate with 1 degree of freedom. It can, in its own system, this is all it could do is rotate by the angle phi. And likewise, the upper arm is the same object, which with a different instance transformation applied to it, and it can rotate in the same way by an angle psi. Okay, so that's known as an articulated model because the parts are connected by simple joints. And if we want to know the state of that model, all I need to do is give you the 3 angles, and you know everything about that model once you know what the base objects are. So it's a very, very simple thing to animate. You just keep changing the angles interactively or through some program control, and then you keep drawing it. Now, if you look at let me show you the model first. Let's do that. Let's look at the model. Let me go to here. And it's on the web. It's called Robot Arm. Clever. Here's the robot arm. I've done this, as I said, with just starting with cubes that I've instanced. Makes it the code very, very simple. So I can rotate the body, that's the base, and it just has a different color on each side. And because of the attachment, it's also rotating the upper arm and the lower arm. I can rotate the lower arm, that's rotating it pretty fast, and I can, let me move see the angle a little better. I'm rotating it, see it has just the 1 degree of freedom, and the upper arm is attached to it, so it goes along with it. The upper arm rotates independently, and the base rotates both of them. So you can sort of make the observation that I can, in some ways, put it this way: the position of the base is completely independent of the upper and lower arms. The position of the upper arm depends on both the lower arm and the base. The position of the lower arm only depends on the base. So there's a hierarchy built into it. That's how we're getting into these hierarchical graph and tree structured models. So how do we take advantage of what we see here in these relationships? So let's look at how we can do that. So let me come back to the PowerPoints and let's argue. So here's what we were just observing. The base rotates independently. I only need that single angle to talk about it. The lower arm now has 2 angles I control it, the angle of the base and its own angle that the hinge makes with the base, and the upper arm is going to depend on all 3 angles. So how do I do that if I'm going to now do a little interactive animation like I just saw you? What showed you? What matrices do I need to do that? Well, let's look at that. Now we're going to get into what we have to store and how we apply the various matrices. So the rotation of the base is just some rotation angle. So the matrix M that I'm going to draw, I think of that matrix M as the modeling matrix that has to be multiplied by some projection viewing, by a viewing matrix. So it's the model part of the model view matrix. So it gets applied to some rotation matrix about the base. Now, if we think of incrementally, then we're going to translate that lower arm up to place it on the base from where it's located in its own coordinate system. So I need some transformation matrix TU, which is just going to raise the y value. So what I'm going to do then is to say, well, and then it's going to rotate by its own angle in its own coordinate system. So what I need, but I have to also realize that that thing is going to also have the base rotation applied to it. So the appropriate matrix to draw that that lower arm is to first rotate it in its own coordinate system, translate the resulting object up by essentially up in our case by this translation matrix TLU, and then apply the base rotation to it. Now I just apply that idea recursively and say, well, look, what about the upper arm? What I've got to do with the upper arm is rotate it in its own system, then translate it up to where it is relative to the base and the lower arm. Well, I have the matrix for the base and the lower arm. It's the rotation of the base times the translation of the lower arm times the rotation of the lower arm. Now I'm going to apply that to the rotation of the upper arm and the translation of the upper arm. So these are the three matrices that, and if we say that we don't worry about the viewer is in the default position, then this is the model view matrix. We have three different model view matrices that apply to the three parts, and I can be careful in how I compute them. Is that I don't have to compute each one from scratch. I compute this when I apply it to the base. I alter it by this translation and this rotation, apply it to the lower arm, then change what I already have, the three on the left, multiplied together, and now I concatenate that with the product of this TUU times RUU. So we're starting to see some structure that I can take advantage of, not only to describe it, but also to make the code much, much more efficient. So if you look at the part of that that's in that code, and look, again, it's under Chapter 9, Robot Arm, here's the exactly what I was just saying. Here's the render function. Now, what we're going to do is that theta is going to have three angles in it. They were the ones that were altered by the slide bars that you saw on the screen. So I get that angle. I rotate the base angle now I'm rotating, it's pointing up. I'm rotating about the y-axis. And now I get a model view matrix when the viewer is in the default position, and I draw the base with that model view matrix. Now I update the model view matrix by multiplying it by this translation and this rotation. This rotation, if you go back, you'll see that the rotation now was about the z-axis in the model coordinate system for both the lower arm and the upper arm. I apply those matrices to the model view matrix. Now I draw the lower arm with that model view matrix. I then do the same thing for I translate by the height of the lower arm. See, I have to push it up the height of the base. Now I push it up an additional height, which is the height of the lower arm. I rotate by around the z-axis by its theta, and now I multiply the model view matrix is again the product of what I had before, the translation, the rotation. I draw the upper arm, and now I just do request a new animation frame. So it's very straightforward. It's pretty efficient here. The only thing, the major thing we've left out is this is kind of linear. You go from the base to the lower arm to the upper arm. It's not, you say, well, what do I do if I have a figure model where I have arms and legs and hands and things, how does this apply? So that's really what we're going to start looking at now. And the way we're going to look at it is to introduce trees. And the tree, you could say, well, this is a really simple example of a tree that we just talked about. You can talk about the base as being the root. The base then has a child, which is the lower arm, and it has a child, which is the upper arm. And that's a tree, a very simple tree. So now, if I'm going to do that with this tree structure and fit that in, what kind of structure do I want to use for each node? And so I'm proposing, and we'll see this in more detail in the next lecture, I'm proposing that we have a node that's something like this, that it's got to have the information we've said about how to draw the thing. It has to have information about relating this node to its parent, and that's an incremental matrix, some sort of a homogeneous coordinate matrix, the sense of what we saw in our first example. And then there's going to have to be some pointer to how many children there are. Now, for a general tree, I don't know how many children there are going to be. There can be none, there could be an infinite number, not an infinite number, but a lot. And so what we will generally do here is put a linked list down here. So if there are no children, there'll be some sort of a null, equivalent of a null pointer or a null here. And if there's one child, it'll have a field here that will say, okay, what's the next child? If that's null, then there's only one child, as in this robot arm, but if there are other children, as we'll see, it'll point to the next child and the next child and the next child until you see a null. So you can see sort of get an idea of what we're going to be talking about traversal, is that every time you hit a node, you're going to draw what's there, and the drawing is going to use this matrix M to relate to everything you've done above with parents, and then you're going to go and start rendering the child nodes. Point to another node, which will then say, which will then tell you how to draw that, and so on. And that's what we're going to see in the next lecture. So the general things we want to look at is how do we represent a more general tree? How do we traverse it? What traversal is going to mean is that we have to, if I have a tree structured model, if I'm going to draw that and there's geometry in every node, I need a way of visiting every one of those nodes so that I can draw the geometry that's stored there, and I want to do that in an efficient way. So we'll talk about general traversal algorithm. And then we want to look at it dynamically, not just in that maybe some angles are changing and the thing is moving around, but also what if the general structure changes? What if I want to add a hand to the end of that robot model, or I have a set of tools that I could put at the end? Then graphically what you're going to see is different, but I want a way to alter that structure dynamically, and it turns out that's going to be fairly straightforward to do, and all of these issues we'll investigate in the next lecture.